Okay, so thank you very much for still being alive at this time of the day. And first of all, I would like to thank Matteo and Lucia for the kind invitation and the fantastic organization of the event. So my name is Marcello Ferrera, and I work at Heriot University in Scotland. And today I'm going to talk about the transparent conductors and the journey of this material platform from plasmonic to time-varying systems. So, as I said, at the center of my presentation is this class of material, the class of transparent conductors, who have been well known by the industrial world because they've been applied for the fabrication of photovoltaic cells and touchscreen devices as transparent electrodes. And this one has been ongoing for quite a few decades already. A few years ago, on the quest for the perfect plasmonic material, the perfect substitute to metals for plasmonic devices, me and my collaborators in the US, we started working with this class of materials. There were quite a few interesting results where certain metamaterials were fabricated, where metallic inclusions were replaced by transparent conductor inclusions, demonstrating that they were good replacement for in plasmonic systems. However, soon after this kind of studies, we realized that when these materials are operated in the near IR spectral window, where the refractive index is particularly low, the optical nonlinearities, so our capability to modulate the optical property of the material represented by the complex permittivity, are extremely amplified. And this is not just related to the magnitude of the effects that we can record, but it is also related to the speed at which these effects can be recorded. So the nonlinear bandwidth is absolutely outstanding. So in general, for those who are not particular into these materials, they are wide bandgap semiconductors that through different fabrication means, they are altered by increasing the intrinsic concentration so much to push the Fermi level into the conduction band. And so they are intrinsically hybrid materials because they have metallic properties, but you fundamentally have still an intrinsic barrier. So, strangely enough, this is a formula that I should not report, but I do it not for upset my colleagues, but fundamentally for two reasons. One, because the original intuition that materials with a very low refractive index can be a good alternative in nonlinear optics came from looking at the simple Boy textbook formula linking the nonlinear Kerr coefficient with the chi3, and where you see that the index appears at the denominator, and so when it is small, then you can imagine that the nonlinear Kerr coefficient becomes quite large. However, that one, this formula has also another interesting aspect, which is for several years, nonlinear optics was searching for the most nonlinear material, looking for the material with the highest chi3. And then instead, when we started working with this kind of systems, we sort of changed direction, searching for material with a low refractive index. And because actually high chi3 are linked to high refractive index, is really like a sort of opposite direction. However, this formula cannot fundamentally be used for these materials for several reasons. Well, fundamentally because this one neglect any kind of dispersion. These are instantaneous bound electron nonlinearities and so on and so forth. and should not be considered a good approximation of the nonlinear property of our systems. So let's talk about a few preliminary results, those that started a lot of discussion behind the nonlinear application of these compounds. So here are just a few that I actually like very much. So the first one is demonstrating how we can change the refractive index, how much the refractive index of this material can change. As you can see, it's massive, not just in percentage because you started from a low index, but it is very large in magnitude. And here we almost show unitary change, but recent works show that this one can be pushed also considerably higher than 1 in terms of refractive index. So you can even easily match the refractive index with of air. This one is another work where we exploited the hybrid nature of these materials, and so we took advantage that we can have interband and intraband nonlinearities, and so we can use a two-color excitation. We can pump interband and intraband inducing opposite change in the material properties. In this case, you see that the transmittance of the material with one kind of pumping is reduced and with the other one is increased. And then you can time these different pumping regime and practically kill the effect in a sort of three-state logic system. This one is an example where in a nano-Fabry-Perot, introducing a 25 nanometer of gallium zinc oxide through optical pumping, we can tune the resonance of this cavity and modulate the output by 80% with on-off time of about 300 femtoseconds. This one is a rigid 48 nanometer bandwidth shift of a transmitted ultrafast pulse of a 40 nanometer performed also optical. And well, these are all the articles related to these results, and you can see that Lucia and Matteo are also present. They played a very fundamental role in bringing this material platform where it is now. Keep giving few extra examples of how performant are these materials in the nonlinear regime. This one is an indirect measurement that we perform of the nonlinear bandwidth. At the beginning, it was a little bit sort of controversial because we measured 268 nanometer, which accommodate a pulse of about transport limited pulse of about 7 femtoseconds, something like that. And then nobody at that time believed that these materials could go that fast. But more recent experiment, some direct pump and probe experiment performed with almost single cycle pulses demonstrate that actually that bandwidth is not just coming from our imagination. Well, this one is another comparison, for instance, of third harmonic generation between our ultra thin films and other flat platforms, well, including perovskite, electric metasurface, plasmonic metasurfaces, and you can see how the performances are considerably higher in our materials. And these are very flexible materials, flexible in the sense versatile, because we can really tune the optical property even through fabrication means, and so we can really set the so-called epsilon near zero wavelength or low index region. In any case, the region where the nonlinearities are maximized on a broad range by fabrication means. About the reason why these materials are so nonlinear, where the story is quite long, but I don't want to annoy or put anybody into sleep. The one thing is that there are two ways to approach the problem. In a certain way, you can look at the problem from a macroscopic point of view or from a microscopic point of view. From a macroscopic point of view, certain works that we perform in collaboration with Jacob Kurgen shows that we can associate the nonlinearity with a sort of slow light effect that happens into this material due to their dispersion. And it is interesting, though, to see that these are similar effects to what you attain with microcavities or with photonic crystal elements, but in this case, they come sort of for free without any fabrication complication. On the other side, if we want to look from, let's say, a macroscopic point of view, these nonlinearities can be associated to the change in the electron effective mass outside the parabolic approximation. But again, the story behind the reason why these materials are so fast and are so linear is actually a quite big story, and it is still a sort of open debate. Oh, sorry. Something is waiting, maybe. Yes, one slide. Okay, yeah. So, yes, sometimes there is still a lot of discussion sometimes because especially from the community of people that have operated for a long time with the standard semiconductor nonlinearities. The question is, okay, what is different with respect to this system? Why the relation with the terminology time-varying materials? And this one is, if you want, another very brutal simplification to sort of explain the terminology behind these materials. And for instance, here we have the Duffing equation to represent bound electron linearities. And here you can see how you have the relation between the driving field and the harmonic generation that you have through nonlinear processes, and instead focus your attention solely on the change in the electron effective mass of hot electrons. So in this case, you look more at the processes due to the free electron plasma, and then you can associate now this kind of differential equation, where now you have a linear system, but is a time varying. A linear system, but because this system now is a non-conservative, substantially energy is not conserved, then it can be also very effective for frequency conversion situation. Of course, the trick here is that you are hiding the reason why what is causing this time change in the plasma frequency, which reset the energy conservation problems. So, and that's why sometimes this is the reason why you can associate this system to time-varying material, to time-varying system. This is also the reason why sometimes people talk about linear effects, although it is debatable if it's linear. Anyway, I am going to show fundamentally the results that involve myself, my team, and my collaborators, but there is a lot of literature out there, a lot of people doing a fantastic job, and definitely this is not an exhaustive list of results. And if I am neglecting anybody in this room, please let me know. I will find some space somewhere here. Okay, it's see if I click again, then it goes okay. So moving towards more recent results. Okay, so again, one thing that is useful for understanding these materials is that it is good to look at them like let's say super metal, if you want, because fundamentally you have a metal where you have a 1 order of magnitude higher chi3 and 3 order of magnitude less losses. So it's a super metal. Of course, 3 orders of magnitude less losses than metal is still quite some losses, right? But still, for integrated photonic purposes, when you can propagate for a few microns, is a lot. Okay, instead of having penetration depth of 10 nanometers. So that's the fundamental difference. And because of that, now you have a system, because you are playing with the electron free gas that is like playing with the plasma, and so it is intuitive that you can have a very interesting effect in the high harmonic generations, and this is one example of a set of results that we published just at the end of 2024. And it's interesting to see how, given the very large nonlinearity, we can also, for angular incident of our pulse, to generate both odd and even harmonics. Okay. Another application, because again, what we are having here is a very nonlinear material. So fundamentally, wherever you are using nonlinearity, you can think to replace your nonlinear standard material or crystal with this kind of compound. So this one is another example. This one is a frequency resolved optical gating system. So it's a frog. It's a system that it is designed to measure amplitude phase of ultra-fast pulses. Without going into the details, fundamentally, it works by having the pulse that you want to measure interfering, having a nonlinear interaction with a replica of itself in a nonlinear crystal, and then you record the nonlinear interaction. Can be a second or third order or a third harmonic signal as a function of the time delay between the two. And from this frog trace, you can, through a very established algorithm, retrieve the information that you want. And in this system, by replacing the standard bulk and nonlinear crystal that is cut for phase matching and for bandwidth optimization, with 250 nanometer of our low index material, we substantially improve by a large margin all the basic parameters of the original system. So bandwidth, sensitivity, and also with the additional advantage of eliminating phase matching requirements because of the deep subwavelength nature of the film. Everything was phase matching by nature. In addition to that, we were able to record both second and third harmonic at the same time, and so we had both second and third harmonic frog combined. And recently, we demonstrate that we can apply machine learning on this broader set of information to retrieve our traces more accurately and with a much higher resilience against the noise, which is a problem in frogs. But everything, how long do I have? 10 minutes, okay. Everything I have shown so far pertains the typical out-of-plane configuration, mainly because, as I said before, we cannot propagate for very long distances because losses are still, let's say, relevant in these materials. But is there a way to exploit these huge nonlinearities over longer propagation distances for extended devices? And the answer is yes. A very straightforward approach is provided by this optical interconnect, where we have a low loss single mode channel, and then we have on top a spacer, and then on top a thin film of our highly nonlinear material. And so you have the mode that is propagating in this waveguide that is evanescently coupled with this thin layer of, in this case, of ITO. And so we can moderate the losses because the field is just confined in a tiny fraction within the ITO. But we also moderate the nonlinearity flows. So it's a trade-off. However, if we redefine, let's say, the typical a simplified figure of merit for integrated devices, where you have the nonlinear coefficient over the losses. This coefficient actually doesn't say much, because the highest value for this is the silica. Simply because if the losses wins over everything and you can propagate for 300 kilometers, you can accumulate enormous nonlinear effects. So, but if you are targeting integrated photonic devices, then you don't have hundreds of kilometers. You want to know for a given length, what is this figure of merit? And so we rewrote it as a nonlinear phase shift for a given distance divided by the losses for that given distance. So we obtain these curves for different important platforms in integrated photonics, and everything makes sense, because you see that the TCOs outperform any other system in this range, from few hundred nanometer to few microns. Silicon nitride has become now the new nonlinear integrated platform for spiral waveguides with a few tens of centimeter length. Again, silica is for very, very long distances. And these interconnects are placed as the most nonlinear system for when you are targeting an all-optical device, a nonlinear device with a propagation length or with a footprint that goes from a few micron up to 1 millimeter. And we speculated that this kind of interconnect and this kind of size can be the core for a new design for all optical integrated neural networks. And we are working on that. Hopefully, I will show you result later. So as I said, these materials are given the enormous refractive index change that can happen also in a very short period of time. They are the closest approximation to time-varying media. One typical example of effects in time-varying media. Can you click on it? It doesn't work here. Is temporal is a time refraction, which is the equivalent in time of what you have in space in terms of a spatial interface. So you just have a radiation that experiences a sudden change of the optical properties in the universe. And again, you have is the dual of the what happened in space. There are some fundamental theories, quite simplified but quite powerful to understand what is happening. That are, for instance, merging the perfect time refraction with the perfect temporal, so spatial refraction with the one unique formula that is a sort of generalized Snell law for these spatio-temporal interfaces. We rewrote this formula for our specific case of the ultra-thin films. And by some simple analysis, we came out with these very intuitive formulas, where from the time gradient of the index, we can estimate what is going to happen to the angle and the wavelength or frequency of a radiation that is trespassing a thin layer of our energized material. That is energized with an external pump. So, this one is going to be tough. Let's see if it works. So if we don't pump the material, of course, nothing happens. By using those formula, instead, if we have a probe that is properly synchronized with the pump, we see that this one breaks in two parts, takes different direction. They carry 98% of the energy. And they are red shifted and blue shifted with respect to the epsilon zero wavelength of the material. So, thank you so much. Okay, so just a few seconds on what we are working about now. This one is a very recent. Not the previous one. Yeah, this one is a very recent theoretical work that was led by Michael Scalora one of our closest collaborator, and in this case is investigating the possibility to use some kind of time lensing effect using an ultra fast pump and a longer probe to generate attosecond pulses using these materials. These one are very recent results where we are investigating the possibility to use these materials in the quantum domain. In this specific case, we look at the emission properties of quantum dots when coupled with the low index materials and when just simply on glass, and we saw a considerable reduction in the lifetime of these emitters, a strong improvement in the saturation properties, and also an increased directionality in the emission cone. And this one is also an article in preparation on APR quantum. And then another work that is in collaboration with Maria Antonietta Vincenti, that has been already very well presented in much more detail at this conference, where again we are just looking at the other transparent conductors options for our studies. And yeah, I guess well, more or less this is everything. For the sake of time, I would just go straight to the acknowledgement. So first of all, I would like to thank the person that make everything possible in the lab. So my former PhD student, Wallace Jeffrey, now postdoctoral associate in my group, and Mr. Sven Stengel, who is a PhD candidate. I cannot show one of these enormous pictures with 20,000 people because it never happened. I would like also to thank Professor Andrea Di Falco from St. Andrews, who has been extremely helpful for the fabrication of the devices. All my colleagues at Heriot-Watt who helped also from few theoretical aspects. Well, Matteo and Lucia again for everything, and also because they are going to be key in the investigation of the quantum properties of these materials. And then again, Mike Scalora and Maria Antonietta Vincenti for their enormous support in letting me understand what we see in the lab. And then also our collaborator in the US, who has been so kind to provide us with these materials. And I thank you all for your attention.